At 485 feet over Panama, a U.S. Army paratrooper whose main failed had less time than it takes to finish this sentence. Some men in the first wave carried no reserve because commanders believed it could not fully deploy before impact. That sounds like removing a lifeboat because the ocean is too rough. But the decision followed brutal logic. Below 500 feet, the second parachute could become extra weight instead of a second chance. The title turns that mission decision into a universal rule. The real explanation was hidden inside a countdown lasting only seconds. Fort Bragg, in the final days before December 20th, 1989. An ice storm had settled over North Carolina as soldiers of the 82nd Airborne Division were called in for what many believed was an emergency readiness exercise. They expected to jump onto a familiar training area and still make it home for Christmas. Then live ammunition appeared. Maps of Fort Bragg disappeared. Officers unfolded maps of Panama City instead. The mission was Operation Just Cause, the American invasion of Panama. Paratroopers would fly south in Air Force C-141 Starlifters, rig their parachutes during the journey, and jump near Omar Torrijos International Airport. Their combat loads included weapons, ammunition, radios, and equipment. The aircraft would be crowded, the target would be defended, and the first wave would cross the drop zone at an altitude of roughly 485 feet. Colonel Charles Kling, then a young engineer officer, later gave the Army Corps of Engineers a vivid detail. His group was not issued reserve parachutes. The reason he remembered was simple. At that combat altitude, there would be no time for a reserve to deploy if the main failed. That is a named recollection from one group, not proof that every paratrooper in the first wave went without a reserve. The doors opened over Panama and the jumpmaster called out that the drop zone was hot. Tracer fire rose near the airfield. One aircraft closed its doors and went around. When the paratroopers finally exited, the change from freezing North Carolina to hot tropical air hit them immediately. Their canopies opened, they had time for only a quick look, and the ground arrived. Some landed in sawgrass higher than a man. Others came down near the runway, fences, swampy ground, and gunfire. This is the historical reality behind the title, but it needs one correction before the story goes any further. American paratroopers were not universally ordered to ignore every reserve below 500 feet. Different units, different parachutes, and different emergencies produced different instructions. Some combat troops jumped without reserves, others carried them at almost the same altitude. Modern Army guidance tells a jumper with a serious malfunction to activate the reserve immediately. So where did the 500-foot idea come from? Start with what a military static line jump is not. It is not the sport skydiving image of a person falling for a long time, checking an altimeter, and pulling a handle to open the main canopy. A mass tactical paratrooper leaves much lower, surrounded by other jumpers, often at night, carrying equipment and moving toward a defended objective. The main parachute begins deploying automatically. Inside the aircraft, the jumper attaches a static line snap hook to an anchor line cable. The other end is connected to the parachute deployment system. When the jumper exits, the static line stays with the aircraft long enough to pull the deployment bag from the pack on the jumper's back. Suspension lines extend, the canopy comes out, air fills the fabric. Only after those stages does the opening shock tell the jumper that the system has done its job. Each stage consumes altitude. Older T-10 fixed-wing procedures taught jumpers to count to 4,000 after leaving the aircraft. Current T-11 fixed-wing procedures use a count to 6,000. Other parachutes and aircraft can require different counts. If no opening shock is felt at the end, the jumper is supposed to activate the reserve. That count gives the main system time to reach the point where an inflated canopy should exist. But on a very low combat jump, it can consume nearly all the time available during a total malfunction. The physics is merciless. Ignore air resistance for a moment and imagine an object released 500 feet above the ground. Gravity brings it down in a little under 6 seconds. A human body experiences drag, and an aircraft exit is more complicated than a laboratory calculation, but the scale is what matters. 500 feet does not give a falling person half a minute to solve a problem. It gives only a handful of seconds. Under the Army's comparison, for a heavily loaded soldier, a properly inflated T-10D averaged roughly 24 feet per second. If the full 500 feet were available beneath that open canopy, the trip would take around 20 seconds. That is enough to check the canopy, look for other jumpers, release equipment, and prepare for impact. A total malfunction erases that slower phase. The same height that feels brief beneath a good canopy becomes almost instantaneous in free fall. Now subtract the time needed for the main parachute to reveal that something is wrong. Subtract the time required for the jumper to recognize the failure. Subtract the physical reaction of finding and pulling the reserve handle while tumbling under a heavy combat load. Then subtract the time required for the reserve to leave its pack, reach line stretch, inflate, and slow the body before impact. That final step is the part movie scenes usually erase. Pulling a ripcord does not create a canopy. It begins a mechanical sequence. On the older chest-mounted troop reserve, opening the pack exposed folded fabric that still had to be driven into clean air. Depending on the model and malfunction, a jumper might have to help throw the reserve canopy away from the body and the damaged main. Suspension lines had to extend without fouling. The fabric had to catch air. The canopy then needed enough distance to convert a near-free fall into a survivable descent. The main canopy usually remained attached. Unlike a sport parachutist cutting away a square canopy high above the ground, a low-altitude static line jumper could need every scrap of drag the damaged main still produced. That meant the reserve might deploy beside, behind, or into the first canopy. Two inflated round canopies could leave the jumper with little directional control. Tangled fabric could be worse. Reserve training therefore covered how to throw the canopy into clear air, not merely how to pull a handle. That is why deployment and deceleration are separate problems. A reserve might begin to open before impact and still fail to slow the jumper enough. Fabric above your head is not the same thing as a functioning parachute. At very low altitude, the body can reach the ground while the rescue system is still becoming a parachute. The key distinction is that 500 feet did not mean the same thing in every emergency. A total malfunction provides no usable main canopy. The static line may have broken. The jumper may not have been hooked up. The main may remain inside its pack. In that case, altitude disappears at close to free fall speed. A reserve pull delayed by even a few seconds may come too late. A partial malfunction can be completely different. A torn or deformed main canopy may still create drag. A streamer is technically a partial malfunction because the canopy has deployed, though it can provide so little lift that procedures demand the urgency used for a total failure. If the damaged main is descending slower than freefall, those extra seconds can allow a reserve to inflate. Modern static line training therefore tells the jumper to check the canopy, compare the rate of descent, and immediately activate the reserve when the malfunction requires it. There is also a third situation that often gets mixed into this story. What if the parachutists are still inside an aircraft that suddenly suffers an emergency? Field Manual 3119, Special Forces Military Free Fall Parachuting, issued in August 1977, drew an explicit altitude ladder for that problem. Below 500 feet, personnel were to prepare for a crash landing with the aircraft. From at least 500 feet up to 2,000 feet, they could exit and deploy the reserve immediately. At greater altitude, the main parachute became an option. That was an aircraft escape rule, not an order to ignore a failed canopy after a normal static line exit. This distinction sounds technical on the ground. In the air, it separates three entirely different questions. Should you leave a damaged aircraft? Has the main failed completely? Or is a damaged main slowing you enough for the reserve to help? The phrase "never pull below 500 feet" compresses those questions into a memorable warning, but it also hides the conditions that made the warning useful. Why operate so close to the limit in the first place? Because combat altitude was chosen against enemy weapons, not just parachute engineering. A parachutist beneath a round canopy is slow, visible, and poorly able to evade fire. Every extra second in the air gives rifles, machine guns, and anti-aircraft weapons another chance. Wind also pushes an open canopy away from the planned landing point. A higher drop can scatter a formation across fields, woods, towns, water, and enemy positions. That delays assembly on the ground, separates leaders from units, and turns a concentrated assault into dozens of isolated fights. Dropping lower reduces drift. It shortens the time during which paratroopers hang as targets. It places more of the unit near the objective and gets weapons into action sooner. The transport aircraft can also approach low, reducing some forms of detection and limiting its exposure while crossing the drop zone. Mass tactical operations magnified every second. A transport formation might carry hundreds of soldiers across one release area, with aircraft following aircraft and jumpers leaving both doors in rapid succession. Raise the drop and a crosswind broadens the landing footprint and increases scattering. Lower it and the formation arrives in a tighter area, but canopies have less vertical space to separate. The altitude decision affected the whole assault, not only the survival equipment worn by one person. But every tactical advantage is purchased with emergency time. The aircraft is safer for a shorter crossing. The formation lands tighter. The paratrooper reaches cover sooner. Yet the reserve loses the altitude it needs to work. 500 feet emerged as a brutal compromise between two dangers, one in the sky and one on the ground. The American airborne experiment had been wrestling with that trade since its beginning. In 1940, the Army formed a parachute test platoon at Fort Benning with 2 officers and 48 enlisted soldiers. These early paratroopers packed and maintained their own parachutes under technical supervision. They were building doctrine while they were learning whether large groups of soldiers could leave aircraft, land together, and fight as infantry. World War II expanded that experiment into airborne divisions. American paratroopers jumped with round main canopies, such as the T-5, whose canopy measured 28 feet across, and later the improved T-7. A reserve was worn on the front of the harness. That chest pack became part of the silhouette seen in photographs of Normandy, Holland, and the Rhine. The scale of airborne warfare also changed who prepared the parachutes. The original test platoon had packed its own equipment. As the Army trained thousands of paratroopers, dedicated maintenance organizations took over much of the packing, inspection, repair, and issue work. A low combat jump depended on those riggers because the main had to work on the first attempt. At extreme altitude, there was no time for a soldier to compensate for a packing error after leaving the door. The reserve offered a real second chance at ordinary training and operational altitudes. It also imposed weight and bulk on a soldier already carrying a weapon, ammunition, entrenching tool, food, water, and other equipment. More important, the reserve still needed time. The lower the aircraft flew, the smaller its useful window became. In England, during June of 1942, the unit that became the 509th Parachute Infantry conducted a mass rehearsal jump from only 143 feet. The Army's own unit history records it as the lowest altitude mass parachute jump. The number is astonishing because it sits far below the later 500-foot line. It does not prove that a reserve could save a man from 143 feet. It proves almost the opposite. The main canopies had to begin opening the instant the soldiers left the aircraft, and there was essentially no emergency margin. The exercise demonstrated what a static line could do under unusually favorable conditions. It was never a promise that a backup system could defeat gravity from the same height. World War II also showed why commanders wanted low drops. Transport formations crossing a defended coast could be broken by cloud, navigation errors, evasive maneuvers, and anti-aircraft fire. Higher altitude increased the distance jumpers could drift after exit. A division planned to land in organized groups might arrive as scattered companies, platoons, and individuals. Scattering sometimes confused the enemy, but it also robbed the airborne force of the concentration it needed. Lower was not automatically better. Trees, buildings, water, rough ground, aircraft speed, and the design of the parachute all mattered. A canopy that opened faster could operate lower, but a violent opening could injure the jumper. A slower, gentler deployment reduced shock while consuming more height. Parachute design therefore lived inside the same argument as combat tactics. Save the body during opening, but open before the body reaches the ground. The argument returned with new urgency on October 25, 1983. Over Point Salines in Grenada, More than 500 Rangers jumped to seize the airfield during Operation Urgent Fury. The Army Quartermaster Museum's official history states that the drop was conducted at 500 feet to avoid anti-aircraft fire from the surrounding hills. The altitude and the reason for it are well documented. The reserve story is less tidy because official battle histories describe the hurried rigging without listing every component worn by every man. That distinction matters. Grenada proves that commanders accepted a 500-foot drop under anti-aircraft fire. It does not prove that every Ranger lacked a reserve, or that every American formation received a permanent order never to use one. What the operation does show is the calculation. The C-130s approached close to the sea, climbed steeply to drop altitude, and released Rangers while fire rose around them. The soldiers had seconds beneath their canopies before striking the runway and nearby ground. More altitude could have improved their emergency options, but it would also have exposed the aircraft and descending Rangers for longer. If this kind of military history is your thing, subscribe. We break down the equipment and decisions that turned ordinary seconds into life or death. 6 years after Grenada, Panama pushed the calculation slightly lower and produced direct testimony for both equipment choices. The first wave of Operation Just Cause jumped from roughly 485 feet. Some engineer paratroopers were not issued reserves. Yet Captain Dave Taylor Jr. told an Army historian that his first wave group from the 82nd Airborne did carry them at about 500 feet. The safety wires normally fitted to the static line snap hook and reserve were omitted, but the rest of the procedure remained familiar. Taylor remembered rehearsing the exit in his mind with his hands on the reserve, feet and knees together, because the ground would arrive quickly. His canopy opened after the 4 count, and only a moment remained to lower his rucksack before landing in deep elephant grass. Klinger remembered a group without reserves because a total malfunction left no time. Those accounts came from the same operation. Together they destroy the idea of one universal 500-foot command. The jump also reveals why a main canopy could work while a reserve was considered hopeless. The static line had already begun the main deployment before the jumper could react. The system borrowed the aircraft's movement to extract the deployment bag and extend the lines immediately. A reserve activated after a failure started later, after recognition and human action. At 485 feet, that delay could be the entire remaining margin. Imagine the sequence without slowing it down. The green light comes on. The jumper hands off the static line, turns into the door, and exits. The line draws tight. The main begins to deploy. The jumper counts. If the canopy opens correctly, the falling body is arrested and descent settles under the round fabric. There may be only enough time to check the canopy, orient toward the ground, release equipment, and prepare to land. If the main never opens, the same count ends in a different world. The ground has grown with every number. The jumper must recognize the missing shock, reach the reserve, pull, clear the deploying fabric, and hope the canopy finds air. The reserve then has to inflate and decelerate a soldier carrying a combat load. At that point, there is no spare step in the sequence. There may not even be enough altitude for all the required steps. The load made the landing harsher even when everything worked. Veterans of the Panama jump remembered soldiers carrying roughly 60 to 80 pounds of combat equipment, while the parachute assemblies added still more. A fully inflated main turned a fatal fall into a survivable descent, but the ground could still break ankles, legs, backs, or equipment. That is why feet and knees together and the parachute landing fall were treated as survival procedures rather than graceful technique. That is the centerpiece of the rule. The reserve was not banned because opening it would always make things worse. It was sometimes omitted because a total malfunction at the planned exit altitude left virtually no workable rescue window. Commanders were not choosing between a main and a reserve. They were choosing between spending more time exposed to enemy fire and carrying a backup that might arrive too late. Training attacked the human part of the delay. Paratroopers repeated exit positions, counts, canopy checks, reserve activation, collision procedures, and parachute landing falls until the responses became automatic. In darkness and wind blast, a person cannot perform a fresh physics calculation. The body has to know what comes next before fear begins an argument. That is why Army instructions sound so exact. Count, check the canopy. Compare the rate of descent. Pull the reserve if the opening shock never comes or the canopy is not carrying the load. Keep feet and knees together. Prepare to land. Each short command removes a decision from the few seconds when indecision is fatal. The reserve still remained useful in many situations. Training jumps were higher. Aircraft emergencies could occur above the low-level threshold. A towed jumper cut free from an aircraft needed a parachute immediately. A partial main canopy could slow descent enough to give the reserve time. Actual altitude over uneven terrain might differ from the number briefed before takeoff. 500 feet was a planning figure, but the Earth below a drop zone was not a perfectly flat measuring table. Equipment also changed. The T-10 family served the Army for more than half a century, but soldiers gradually carried heavier combat loads than the system had originally been designed around. The T-11 became the first broad modernization of the Army's tactical personnel parachute system since the 1950s. The T-11 main uses a cross-shaped canopy and a deployment sequence intended to reduce opening shock and oscillation. Under the Army's comparison for a heavily loaded soldier, it averages a descent rate of 19 feet per second, compared with 24 feet per second for the older T-10D. That difference reduces landing energy, though no round canopy turns a combat jump into a soft elevator ride. The T-11 reserve was also built around the low-altitude problem. The Army's equipment description says its design derives from a British low-level parachute. Apex scoop pockets and skirt assist lines promote fast opening during low-speed malfunctions. An omnidirectional center pull system makes activation less dependent on the direction of the reach, while the harness spreads opening force along the jumper's body. None of that makes altitude irrelevant. A faster reserve still has to deploy, inflate, and decelerate. Modern airborne school therefore gives students more room. The standard fixed wing jumps are commonly made from about 1,250 feet. Students complete 5 jumps, including jumps with combat equipment and a night jump, after weeks of practicing exits and landings on the ground and from towers. That school altitude should not be mistaken for one universal combat minimum. Tactical limits depend on the aircraft, parachute system, mission, terrain, and governing procedure. A published minimum also does not prove that a reserve can recover every total malfunction there. The difference between a school jump at 1,250 feet and a combat drop near 500 feet shows how much emergency margin a mission may sacrifice. Modern doctrine also exposes the biggest flaw in the word never. The Army's static line manual says that a jumper who feels no opening shock at the end of the prescribed count should immediately activate the T-11 reserve. It also says to activate the reserve if the jumper cannot compare descent with others or is falling faster than fellow jumpers. The response is based on the malfunction, not on a blanket prohibition below a round number. Army engineers have even tried to remove human delay from the equation. In 2002, the Army Soldier Systems Center described a prototype automatic reserve opener for low-altitude static line troops. Sensors would detect the aircraft exit, begin a 4-second countdown, and activate the reserve if the expected opening shock did not occur. The project existed because ordinary automatic openers designed for high-altitude parachuting were too slow for a 500-foot jump. There was barely time to sense the fall, decide that the main had failed, and deploy the backup. An Army Safety Center review covering 1974 through 1999 suggested that an automatic opener might have prevented almost 1/3 of airborne fatalities. But engineers also had to prevent false activation inside the aircraft or while a jumper was being towed, where an opening reserve could create another disaster. That engineering problem captures the whole history in miniature. Open too late and the reserve cannot help. Open at the wrong time and the reserve can endanger the jumper or the aircraft. Wait for a person to decide and human reaction consumes precious height. Automate the decision and a sensor must correctly understand a violent event that lasts only seconds. 500 feet was never a magic wall in the sky. A parachute does not read an altimeter and stop working at 499 feet. The real boundary moves with the aircraft, the jumper's vertical speed, the combat load, the type of failure, the reserve design, the terrain, and how quickly the problem is recognized. That is why the 500-foot shorthand sounds absolute. Mission planners need a clear altitude, while jumpers need immediate procedures for the malfunction actually in front of them. Nobody can work through every branch of an aerodynamic decision tree while an aircraft is taking fire. A simple threshold can compress complicated risk into action, but it can become misleading when repeated without its original context. In Panama, some commanders decided that a reserve below the planned altitude offered too little chance to justify carrying it. In Grenada, rangers accepted the same general height to reduce exposure to anti-aircraft fire. In an older aircraft emergency manual, 500 feet marked the point below which troops stayed with the aircraft. In today's static line training, a serious canopy malfunction still demands immediate reserve activation. All of those facts can be true at once because they answer different questions. Airborne leaders were not ignoring safety. Combat forced them to compare forms of danger that could not all be removed. Jump higher and the reserve gains time, but the aircraft and paratroopers remain exposed longer. Jump lower and the force lands tighter and faster, but a total malfunction becomes almost impossible to survive. Add more equipment and the soldier reaches the fight better prepared, but every extra pound increases the energy the parachute must control. The reserve on a paratrooper's chest therefore represented more than a backup canopy. It represented time. During training, there was usually enough of it. During a partial malfunction, the damaged main might create more of it. During an aircraft emergency above the threshold, it could save a life. But during a complete failure on an extremely low combat drop, the reserve could not manufacture the one thing the mission had deliberately taken away. So the answer to the title is narrower and more unsettling than the legend. US paratroopers were sometimes told not to depend on a reserve below 500 feet, and some assault forces jumped without one. A reserve required deployment distance and deceleration distance that a total malfunction did not leave. That emergency margin had been sacrificed to reduce enemy fire, drift, and scattering. At 485 feet over Panama, that trade was no longer theoretical. The doors were open, tracers were rising, the paratroopers had a mission on the ground, and the aircraft could not give them more sky without giving the enemy more time. Below 500 feet, altitude had stopped being height. It was time, and there was almost none left.